Welcome to one of the last new analyses we'll present for this semester. This is an extension of correlation as promised, known as regression. And this is based on, again, some of the same things that we talked about with correlation, relationships between two variables, and then subtracting, not necessarily talking about comparison of means, but subtracting one variable from another and seeing what the difference is. And before, we called that the sum of products. With correlation, here we're going to be talking about something called residuals, but basically just trying to see how are variables related in terms of how much of the variance of one can another explain, and how much of the total error is left over that is unexplained. So a lot of those things and more coming in terms of our just a quick overview. We could do a lot deeper dive, but I think for our purposes, we're going to keep it fairly straightforward and on the surface level. Quick review of correlation. Pearson correlation is a linear relationship and using it for generally two continuous variables. Also, to think about a correlation, it tells us the direction of the relationship, either the positive or negative relationship, and as well as the magnitude or the effect size of that relationship. The scatter plot, sometimes it's easy to skip if we're collecting a lot of data and finally get it into our spreadsheets and want to do the analysis, but it's important to look at the scatter plot to know, first of all, where are outliers, and you can see the general pattern that the dots take on the scatter plot and see if there's some dots that really aren't fitting with what the general pattern for the other ones is. And it also can help us to look at the shape of that pattern. Is it indeed mostly linear, or is it a nonlinear, oftentimes U-shaped shape that we have to then consider, is it still appropriate to do the Pearson correlation? A couple things to consider about the use of R. First of all, outliers have a really big impact, and so we need to think, if an outlier is there and it seems like an error, or it seems like something happened with that person and they don't belong in our data set, then we can just not include them. But if it seems to be legitimate measurement on both of our variables, even though it's that one or two outliers are going to draw down the magnitude of our correlation, we still can't just kick them out of our sample because we don't like it. There's other limitations to the use of R. First of all, range restriction. A lot of times the data we get don't represent the full variability in the population, and especially if there are some selection effects, we're only getting data from some people in our ideal population, but only part of that in our sample. That means we know that the correlation we get, first of all, is probably not going to be as big as if we could get the data we want. And finally, sample size really matters with correlation. So it's really easy to look at a scatter plot with 10 dots and think you see a pattern, but you really have to calculate that value. And oftentimes with only 10, even though it sure looks like there's a pattern, the sample size is just not enough to get past the statistical significance threshold. And finally, R squared is a very convenient measure of effect size. It essentially the amount of variability or percentage of variability in one variable that the other variable in the correlation accounts for. Let's look at a quick preview of what we're going to cover today. Basically the different steps of regression, and that comes after we've covered some of the building blocks of regression as well. The logic behind regression is essentially asking questions, usually involving prediction of some level. And correlation is sort of getting there. So is something related to something else? Again, continuous variable, practice time related to continuous variable of team performance. And we know that with a correlation, we can say that yes, one thing, if it's a significant relationship, we can order those variables either way. I mean, hopefully there's one way where it makes more sense, but you can switch our terminology for saying variable y looks like it's predicting variable x, or variable x looks like it's predicting variable y. With regression, on the other hand, here we're formalizing that relationship, and we're specifically saying, with this analysis, one is the predictor variable and the other is the variable that's being predicted. So with correlation, that predictor outcome can go either way, and it's mostly based on just how we're phrasing what we think is predicting the other. With regression, we've clearly identified one as the predictor variable and one as the outcome variable. So let's look at, in terms of basic scatter plots again. Regression is taking a scatter plot, and remember, looking at scatter plots for correlation, saying, well, imagine if you could draw a line that you think best represents the shape of this cluster of dots. And again, if it starting from the lower left-hand corner going up to the upper right-hand corner, we say it's positive correlation. If that line tilts instead downward as we move to the right, then we say negative correlation. Basically now, we are saying specifically with these data, this has to be our x value on our x-axis. This is our predictor, and then our y is our outcome, or sometimes we'll call it a criterion variable. And essentially, this line is, if we don't know, we run a regression where we have values of both predictor and outcome, and then we figure out from that data we have of measures on both the predictor and the outcome in the sample, we get the best line that we can from the sample we've got. The extension is, now that we know that line, and we'll have a formula for it, now we can say, well, now we can use this for people who we don't know their outcome yet, but we've already collected predictor outcome data for one sample, and for people who seem like they are similar to the people in our sample, new people, we can just measure their x variable, and then we predict whatever their x variable is, what their y value would be based on where that x lines up or meets this regression line. So that's the whole logic of regression. And you can see, just like most correlations are not perfect correlations, they don't line up exactly on this line. In our sample, to calculate the line, we can see a lot of these dots, though very close to the line, it's probably pretty strong correlation. It's not a perfect correlation because some of these dots are predicted y is a little bit lower than we'd think, and other of these dots are a little bit higher, our predicted y value, than we would have thought. So this line is the best line we can draw, but it's not perfect as well. So if we're thinking about specific examples, here we have SAT data, a test predicting, and why we pay money to use it is because lots of research has already shown that clearly it's not a perfect predictor, but higher scores on SAT predict higher GPA performance and other things like graduation rates and later income, I imagine, other outcomes as well. So now that we know the company SAT has done the research to show that this relationship is here, I feel comfortable having my students or my children take the SAT knowing that their performance on that will not be a perfect predictor of how they do in college, but it will be at least a trustworthy predictor, and among probably other variables too that are important to consider in terms of how a kid or a student or a child is predicted to do in school based on SAT. It's only part of the story, but this shows I can trust that that story, that part is useful. So our logic behind regression is saying our regression line does not perfectly predict the y. So what is that? Well, that level of imperfection is known as residuals. And essentially, you can take the actual y value, compare it to what the predicted y would be based on this x value, and that distance is what's known as a residual. How far off was the actual value from the predicted value? And what you can do is just add all these residuals up to get the sigma or total of these residuals. If we add up all our misses, how big is that value? And what the regression equation does is essentially finds the line and messes with the angle and the slope to come up with the line that minimizes, that comes with the least residual possible. So again, not perfect, but the least residual, the least error that can be attained is what that line and the slope of that line looks like. So this means we have a regression equation. And again, keep in mind, how do we get this equation? We need to have a sample with both the predictor and the outcome variable, and then we can use this correlation logic, come up with our best line, and once we get this equation, then after we've collected our initial sample to get the equation, we can then use the equation or generalize to other people who look like in our sample we might just have the X value on and say, well, you haven't graduated college yet, so I don't know what your GPA is, but I know your SAT, and I know it predicted before fairly well, so I'm going to generalize that since I only know your SAT value, I can predict with some confidence your Y value or your later college GPA, for example. And these two pieces are basically B is our slope of the line, and the A is the y-intercept, at which on our scatter plot does that line cross the y-axis. And of course the B is the slope of the line, and I noticed some other textbooks and maybe other statistics classes use some slightly different notation. Sometimes I've seen y equals mx plus b. For here we're using y equals bx plus a, but the most important thing is that the one next to the x value is always going to be the slope, and then the one that's by itself afterward is then going to be the intercept. Take your x value, apply it to these slope and intercepts, and then you can get your predicted y. So a previous book example I've used is a tennis club membership versus hour of court time. So you don't get time on the court unless you have that membership first. So you're trying to think about, if I want to do 5 hours of court time a week, how much am I going to have to pay? Well, the intercept is that line, and again, you're trying to predict how much am I going to have to pay? What's my predicted y for that month? Well, you have to have the monthly membership first. So that's our y-intercept, and it's not 0 because you can't get court time if you don't have a membership, if you haven't paid any yet. So maybe you have to pay $50 for that month for the membership, and then another $50 for each hour of court time. And of course, this is the variable x. Well, my variable is 5 if I want to do an hour of court time a day, weekday. 5 hours times the fee for the hour plus the fee for the membership. So again, the intercept is often viewed as a constant in terms of, does everybody start negative or positive or at 0, and then how much you're standing on an individual variable is factored into the slope. And of course, lots of examples, anything involving sort of a bare minimum is usually what that intercept's going to be. So SAT score, nobody gets a 0. The lowest score you can get is a 200. And so what's my predicted score? Well, it's going to start at 200 and then plug my actual score into the slope, and that will give me my predicted score for the GPA. So let's think a little bit about the equations following the logic behind regression. As I said before, logic of regression is that it finds the least squared error solution, again, that line on the scatter plot that leads to the least residuals possible. So we start with this idea of the sigma of the residuals squared, and the regression equation is going to find the lowest sigma residuals squared, or what this equation here is doing. And again, this little hat over the y says that we got this equation, our slope and our intercept, based on our sample data with predictor and criterion values, but now we got the equation. We're just going to take X values, pop new people in here, and come up with predicted outcome or Y values. So we also have another couple of components to consider. How do we get that slope? Well, first of all, we take our sum of products, and notice this is the numerator for our correlation. It's still important, and essentially it's saying the shared covariance between our two variables, predictor and outcome, over the variability of our predictor variable. And that's how we're going to get our slope for our equation. And then our equation for our A, or our intercept, is essentially once we've calculated our slope, we can take our mean of X, mean of Y, and basically that is the formula for our two components for our regression equation. So let's put it all together. And again, this exam is not going to be heavy on the actual equation, plugging and chugging in terms of using it, but it is important to know the equation and to know what the pieces of the equation are. Which is the slope? Which is the intercept? What do they mean? How do we get there? So if you can answer those questions, you're in great shape. Of course, again, our X and Y, X is typically the predictor. That's on our X-axis, and our criterion or our outcome, I use those interchangeably, is our Y variable and our Y-axis. And again, our definition of our intercept, our Y-intercept, is what is the value of Y when X equals 0. So that means, again, going back to the SAT example, what is my predicted Y or GPA going to be when my SAT score is 0? And again, because SAT can't be 0, it starts at 200 for the very lowest. That means if my SAT score is essentially nothing, well, it means I've started at 200, and that is going to be my predicted value if I haven't taken the SAT. And of course, then our slope again is for a 1 unit change in X. So for example, if instead of reserving 10 hours of court time, now I'm reserving 20 hours, how much is the slope, or the dollars per hour? And of course, that dollars per hour multiplied by 10 versus 20, I'm going to have a lot more predicted amount to pay in my court time the more hours I register for. Another classic example in the employment selection context is lots of predictors we can use that are generally validated, and we know previous research shows that they can predict job performance. So now we can take that test and just use the test for new people coming in. We know it's worked in the past for people who might look like people in our actual sample. These new people, since we've already got that equation and our scatter plot line for our least squared residual performance, we'll take new people, give them the cognitive ability test, and then we can predict what their job performance is. Of course, before we've hired them, we don't know what their actual job performance is, but this test has shown to predict in the past, and so because of that, we can be certain, to a certain extent, to trust that that prediction will still happen in the future, just using that equation before we've actually hired the people. So further logic. Points to remember about regression. Basically, least squared error technique averages over and under predictions. So sometimes you miss by your predicted value, or the actual value. Think about the scatter plot being above the regression line. Sometimes it's below the regression line. And those predicted values will never be perfect unless there's a perfect correlation to start with. So instead of saying, oh, I demand perfection and I'm not going to be able to get it, so this isn't useful to me, it's instead saying I know there's going to be some error, but part of the logic between correlation And regression is thinking about how people are different in so many different ways and so many different variables, and trying to take all of that, what looks like noise, and then using these techniques to see, nope, some of that noise is actually, it goes with other noise. And so now that I understand it, it is important relationships that I've pulled out from this giant variability of all these numbers of all these variables. So basically, finally, regression equations should not be used to predict data outside the X sample range. So that means if you had range restriction on your sample to get the regression line and equation, whatever that sample range for X, that means I shouldn't be using something outside that when I'm using the equation later. So for example, if I never had somebody with an actual SAT score of 200 in my validation sample, that means I should, if somebody scores that and is applying to my college, I shouldn't include them. I could still consider them as a candidate, but I can't use my regression equation. So then you get some interesting practical issues if you actually hold people accountable for this expectation. But this is in a perfect world. If you have a range restricted sample for your validation sample, once you start using that regression formula, you have to be careful not to take in predictor scores or plug in predictor scores into that formula outside that initial range, which means that when you're doing your initial sample, your validation sample, try to get as big of a range as you can. Try to reduce the potential for range restriction wherever possible. We also have this idea of the standard error of the estimate. So again, we're talking about this idea of residuals relative to covariance, and typically there's a standard error. Now we're going to talk about significance tests. We're putting things on a distribution of means. We're moving from a standard deviation of individual scores to a standard error. And so now what does that mean about this estimate thing? So basically, we have a standard error of the estimate formula, and just like the standard error of the mean, especially for t-tests or our z statistic, basically in this case, we're taking our error term, our total error, residuals, those values that were not exactly lined up with our predictor line or our regression line on our scatter plot, and we can't explain why one dot was over-predicted, the other was under-predicted. It's just residual from our predicted value. It's off by a certain extent, and we can't explain it. So we then include it in our error or not understood term. So basically, there's two ways to think about it. Sum of squares residual is what we'll normally look at. But if we want to go back, how do we get to sums of squares residual? We can see here is our formula. So again, for each y value, there's what the actual y was, and there's the predicted y along the regression line. We take that difference, we square it for each person, and then over the people in our sample, we add those all together, our sigma, and then we divide it by n minus 2. In this case, degrees of freedom, where we have regression of one predictor, one outcome. Similar to our correlation, our degrees of freedom is going to be two variables involved, so our degrees of freedom is n minus 2 for a one predictor regression. So once again, hopefully you're thinking about some of these concepts. We can get our standard error of the estimate with thinking about our sum of squares residual. We can also think about it in terms of the R squared. So basically, R squared is the amount of variability that one variable accounts for in the other. And one would be, well, this variable accounts for all the variability in the other one, and then we just subtract 1, and there'd be no residuals if it's a perfect correlation. 1 minus 1, if 1 is our R squared, take a correlation, a perfect correlation of 1, square it, gives 1. 1 minus 1 gives us no residuals. But Oftentimes, and in fact, almost every time, that's never the case. And so what we have is our total variability of y, and we multiply that by the total variability representative 1 between the variables minus how much variability is accounted for by our predictor variable, and that gives us our residual. So two different ways to think about, two equivalent formulas to think about sum of squared residual. And again, these aren't all equivalent formulas because this is a standard error of the estimate. We have this denominator part, degrees of freedom, but essentially sum of squares residual can either be this equation or it could also be this equation as well. So if we think logically, if r equals 0.8 and sum of squares y equals 1, we would square our r to get our r squared, and that's what 1 minus 0.64 times 1. So that would give us 1.36, or 0.36 for our sum of squares residual. So simple math, and that's how we get our residual. Again, for a high correlation, we get a small residual. If that correlation is a lot smaller, 1 minus, let's say, 0.25, then we get a bigger sum of squared y. So once again, this is what's known as similar to ANOVA, but again, instead of having one discrete variable, group 1, group 2, group 3, time 1, time 2, time 3, here we're partitioning variance in terms of two continuous variables. So the standard error of the estimate gives us an idea of, we have our sum of squares residual, and how much of that is by chance. That's kind of our standard error. Another way to think about it is we're dividing our sums of squares into two components. And essentially, we're trying to predict y, and we have our r squared times our sums of squares y, our variability in y. This is the sum of squares regression. And this is essentially how much of the variability or our sums of squares is accounted for by our predictor variable. And then the opposite of that is how much is not accounted for still when we factor in our predictor variable. How much is still left over in our y versus predicted y difference that is residual. We can't account for or explain it based on the other variable or variables in our model. So that leads to what's known as an analysis of regression. And basically, how do we do the significance test? Well, basically, we've got our slope and we've got a standard error for it. Now, we partitioned, we got our sum of squares residual, sum of squares regression, and is that slope significant? And we go back to familiar analysis of variance territory. So here we have mean squares, and for our NOVA, we would have mean squares between over mean squares within. Now in this case, we have mean square of our residual, the difference between y and predicted y that we can't explain versus the mean squares of regression. How much of the variability in y is our x or our predictor accounting for? Getting the mean square is basically a similar logic. So we need how do we get this mean square regression? How do we get the mean square residual? Well, we got to go backwards, and we have sum of squares regression over our degrees of freedom regression, sum of squares residual over our degrees of freedom residual. And if you're remembering back to analysis of variance, if you're thinking that looks like values in our analysis of variance table, you are exactly right. So here's what's called an analysis of regression. It's just doing an analysis of variance using the F ratio, using mean squares numerator, mean squares denominator, except with our regression components. So this analysis of regression source table, again, we have some basic logic. If we have a predictor, one predictor, this is like how many groups do we have in our analysis of variance? Is it 4 groups? 4 means we're comparing, or 4 times? In this case, we just have one predictor variable, so our degrees of freedom for the regression, the numerator of our equation is 1. And once we get to our total, usually it's just n minus 1. So here we'd probably have total degrees, or total sample size of 5. And then 5 minus 1 gives us our total degrees of freedom. And then our residual would be basically our degrees of freedom regression plus residual have to add up to our total. So if we figured out a regression and we figured out degrees of freedom total, the difference between those two has to be our degrees of freedom residual. But that doesn't have an obvious explanation for why, in my mind, that's 3. It's just because the math for the other ones determines that value. And how do we get our F ratio? Well, we're looking for mean squares regression. So mean square or sum squares divided by degrees of freedom regression gives us 25.6 in our numerator, mean squares regression, and 14 divided by 3. Let's just round that out to 5. So we have 25 divided by 5, which would give us an F ratio of 5. And if you remember, our F ratio, if it's 5, is a good likelihood that that would be significant. And again, we'd have to consider the degrees of freedom between and the degrees of freedom within. So our F ratio would be F 1, 3 of 5. And we'd have to officially verify on our F table if that's significant, but in most cases that would be. But this is a really small sample size, so we'd have to verify for sure. And we've been discussing a lot of this logic with the idea and hinting, sometimes subtly, sometimes not so subtly, that there's a lot more you can do with regression than what we've shown so far. And that is the concept of multiple regression. Essentially, multiple regression is multiple predictors. So instead of just having one predictor trying to predict a criterion or outcome, here we can have multiple. And notice we don't see any limits. The only issue is in terms of like degrees of freedom, you can't have more predictors than you have people in your sample. So you have to be careful there. But if you're getting a decent sized sample of, let's say, 50 people, there's not going to be many cases where you even think about having 50 predictors. Once you start getting into double digits of predictors, you probably have a more complicated model than you would ideally want. So basically, as an analysis of variance, we can use multiple regression to analyze multiple IVs. Just like analysis of variance, again, we only covered a single factor, but you can have multiple factors, multiple predictors in analysis of variance. The only difference is analysis of variance requires discrete predictors, group 1, group 2, time 1, time 2, whereas regression can include discrete predictors, males and females, but also can predict or include continuous predictors at the same time. And that is the main difference between thinking about multiple predictors versus or comparing regression to analysis of variance. The other thing we haven't covered much, and I'll need to cover more in future classes, is the idea of if you have multiple predictors or multiple factors in ANOVA, you have this idea of interactions. And the idea is that just like with cooking, or you can think of sports too. Think about a great dish you've had. It's probably not just a combination of, well, it has this amount of salt, it has this amount of pepper, and I like salt, I like pepper equally, and I just keep adding things I like until it's a good dish. No, some flavors accentuate other flavors. Some flavors actually make the other flavors worse, and they're working together as kind of the definition of an interaction to make the overall experience multiplicative or much tastier than just the individual components. Or if we think about basketball, you can have a guy who is really good at passing and a guy who's really good at scoring, but then if you combine that person, those people, with a person who's really good at playing defense, you'd say, well, the person's rebounding is worth 5 games out of a 50-game schedule, the person's scoring is worth 8 games, and the person's defense is worth 3 games. But you add them all together, and it turns out they're like a 45-win team, which is a number greater than just adding up what we predict their individual contributions would translate into wins. So that's the idea of interactions. Obviously, we're not going to do the math for those because they get complicated very quickly, but I think you hopefully conceptually can think about how an interaction, first of all, you got to have multiple variables to look at their combined influence, and then be looking for, is the predicted value I get looking like non-interaction, just, well, this variable has this effect, this variable has that effect, added together, and I get my predicted value? Or do I get an interactive effect where my predicted value is a lot higher than just adding in the effects, or is it even lower than I'd predict by one effect canceling out what I predict the other effect would have? So lots of kind of abstract thinking here, but if you go on in statistics and you go on in research, you're definitely going to be looking at a lot of the potentials, extensions of the basic coverage of regression that we've covered so far. So as we start to wrap up, previous book example would be IQ and SAT in predicting academic performance. So again, we have 2 continuous predictor variables, and then we have our continuous outcome variable, academic performance, usually GPA or the prestige of the college that you get admitted to, for example. We can think of a sports example too, IQ plus bench press plus 40-yard dash time in predicting professional quarterback performance. And one way is to think about through Venn diagrams, and the idea is, well, we have 3 continuous predictor variables here in predicting professional quarterback performance. What if these 2 physical ones are kind of sharing a lot of overlap on the Venn diagram, meaning that they're both independently predicting pro quarterback performance, but when you put them together, they're so highly correlated that essentially they're predicting the same thing. So in fact, then the regression might show us, the multiple regression specifically, that it's not useful to include both of these variables. Or it could be that IQ by itself looks like maybe it's not a good predictor, but when you include it with these other variables, you can have what's called a suppressor effect. So it was suppressed when it's just by itself, but you include these other variables, and now it looks like it is important in predicting. And so again, those Venn diagrams of overlapping circles are always very useful with multiple regression. And so basically we have our y variable, which is essentially the circle about the variability of y, and then our big R square. Notice this is big R, not small r. Small r is just with one variable accounting for variability in another variable. Big R square is only through a multiple regression where you have not just one variable, one predictor, but a set. So R squared would be as a set, IQ, bench press, and 40-yard dash together, how much variance in our outcome, QB performance, does this set of predictors account for? And that's what would give us our big R squared. So hopefully you've kind of opened your mind a little bit to the possibilities. This is oftentimes what you'll see in a lot of research is multiple regression with continuous type psychology variables. So hopefully you'll see these in the future, and hopefully you've got enough information to at least be interested and wanting to dig in more to figure out what the results are truly saying about these combinations of variables that regression unlocks. So more to come, but hopefully it's rewarding from where we are so far.